So what we're going to be talking about in this video is we're going to be talking about limits of functions of several variables and also continuity when it comes to functions of several variables as well, or maybe we'll do that instead of a later video. We'll see. What I primarily want to talk about though is in terms of limits, I want to talk about basically the idea of a limit is going to be somewhat similar in a function of several variables as it is in a function of a single variable, but what's going to end up becoming different is how we kind of think about approaching the limit approaching for the left-hand side and the limit approaching for the right-hand side. So let's talk about when you were first learning in calculus, you talked about limits, and there was, if you remember, there was a requirement with limits that the limit had to be the same coming from the right-hand side as it came from the left-hand side. Okay, and then they had to, they didn't have to meet. Like there didn't have to be a point there. It just had that the limit had to be the same coming from both ends. And if it wasn't, then you actually didn't have a limit. Well, when we look at functions of several variables, we're going to have somewhat of the same requirement. And that's something that I want to kind of keep you thinking about. That requirement is that we're going to have to be required to have the limit be the same no matter which direction the limit is coming from, right? The difference here, though, is that on the real number line, when we look at the limit of a single variable, it's just a single line. So all you've got is right and left. When we talk about limits from the perspective of functions of several variables, you now no longer just have the right and left. You actually have lots and lots of paths. In fact, an infinite number of paths. Because you have your functions of x and y. And so remember, when we talk about the domain of this function of several variables, we're talking about the entirety of the xy plane. And so you can kind of imagine that that domain is a region in that xy plane, and we can come in from, you know, the line y equals x. We could come in from along the line y equals x squared as a parabola. We could come in from y equals 0. We could come in from x equals 0. We could enter into that particular point, whatever the point we're looking for the limit of, okay, from a lot of different directions. And so consequently, what we're going to need to do when we're actually trying to figure out whether or not we have a limit or not is we're going to have to determine whether or not that limit is the same coming in from all of those directions. Now, we're not going to get really too hardcore into how we do that algebraically. What we're going to do is we're basically going to look at a couple of different examples and a couple of different canonical paths that we could actually look at the limit from and take the perspective of where we're going to look at the limit from. And from that perspective, we're going to see, okay, whether or not we actually have the limit and the limit exists or it doesn't. Okay, after you actually check it for a couple sets of paths, you should be pretty much done with figuring out whether or not you have a limit or not, okay, at least for our purposes inside of this course. Okay, so here is, first we're going to start out, when we talk about this limits, we're going to get into some of the technical mathematics, and then we're going to move away from that and actually do some problems and things like that. But I want to get at the concept and this idea of the limit and why it is that we do the things that we do in order to actually find a limit of a function in several variables. So we're going to start out with this idea of what we call an open disk. All right, we're going to see open disks quite a lot inside of this course. All right, or we'll see open regions. And what an open disk is, or an open region, is it is a disk. We've got something that's centered at AB, and it's defined to be an open disk of radius delta. Centered at AB, and what we see here is you see something that looks like this, okay? Now you'll notice that that's the equation for a circle, okay? We've got xy belonging to R2, that is, R2 is a set of tuples, right? And these are all the values xy that give me this particular circle, right? I've got a center at AB, I've got a radius of delta, and there we go. Now, by the way, you'll notice something else here, and I'm gonna actually just do this really quickly in here. I'm going to get delta. If I take this, delta will end up being the square root of x minus a squared plus y minus b squared. Okay? And what you see there is we see that this is going to be the region that has all of this common distance, right? That's what a formula for a circle is, just in general. So everything that is this distance away. This will become important when we start talking about things in 3 dimensions. And if you are working in math and you do more work in math, you're going to notice things that are in 4 or 5, and it doesn't make any sense to talk about them even as spheres. Instead, it's just what we call a Pythagorean distance. Okay, and that's what that is, a Pythagorean distance. And in 2 dimensions, that's a disk. So let's just imagine what this looks like. Okay, let's suppose that delta equals 1. Okay, and we're going to let AB equal 0, 0. All right, so we're going to have a disk centered at 0, 0, okay? And it's got a radius of 1, and there it is. Now, I'm going to say it's an open disk, and actually, this is important. It's an open disk, so what we're going to do is we're going to create a line here, and that line is called the boundary of the disk, okay? For the most part, that doesn't play a huge role, at least inside of what we're doing here in Calc 3. That whole idea of like this dotted line open disk. It does play a role when you get into like later stages of analysis, and it ends up becoming kind of important because we want to know what happens if you're actually on the boundary of that disk. We might talk a little bit about that today. But for our purposes, we just want to get the idea of like, I can make this as small as I want to or as big as I want to, okay? And then I'm basically going to have everything that's within that open boundary. All right, so everything that's within here, okay? Now what's next for us is to look at the definition of a limit. All right, so we've got let f be a function of two variables, x and y. The limit of f of xy as xy approaches ab is L, and we write that as the limit xy approaches ab of f of xy equals L, just like we did when we were doing limits before. But notice now we have the Cartesian duple, okay, or the pair, and we're going to that point AB, which is the center of our disk. Okay, that's the center of our disk, so the point at which we're evaluating our limit is going to end up being the center of the disk. So for each epsilon greater than 0, there exists a small enough delta greater than 0 such that for all points x, y in the disk around AB, except possibly for AB itself, the value of f, x of y, is no more than epsilon away from L. Using symbols, so like basically what we get here is we get something very similar, right, to that limit definition that we've had in the past, all right? And things to notice, epsilon is arbitrarily small. We can make this thing as small as we want. So we want to get, okay, if we get arbitrarily small to the limit, we get our function close to the limit, all right, then we know that there's also a delta that's within this disk, okay? So if you kind of imagine here, we've got a disk, okay? Here's our disk, and let's just imagine it's centered at AB. So we'll make this AB right here. And it's got, and that's our center. And it's got a radius of R. Take it radius R, so we'll imagine that this is the radius R, okay? And if you remember when we were talking about functions of several variables, or somewhere around there, I know it's not the greatest circle in the world, but whatever. All right, and so now we imagine, okay, so here is, basically let's think about this as our z-axis, or f of xy equals z. That's the z-axis. So our domain, if I select a value here inside of this open disk, this is some distance there, okay? I've got some distance there. And I'm going to imagine, okay, here's my limit. Okay, there's my limit. All right. If I go epsilon away from that limit, okay, somewhere epsilon inside of that limit, all right, and say, for example, this is f of xy equals L plus epsilon. I'm going to end up inside of this open disk, right? There is some delta in there. I've got that delta. I'm going to end up back in the open disk, okay? If I pick anything, right, that's within this, say, for example, this delta, all right, anything that's within this delta distance here, or delta equals R, it's going to actually then map somewhere into the plus epsilon or the minus epsilon. Very much like that Calc 1 idea, okay? Right, so that's kind of our idea when it comes to the limit. Now, it's a little hard to think about because we're thinking, okay, here's my domain, right? There's my xy axis, right? Here's basically my z-axis, and I'm mapping pairs into this region, and I'm saying, okay, well, if I'm anywhere around on this number line within epsilon, then I know that I'm going to end up becoming within delta inside of that disk, inside of that open disk. Okay, so it's a little hard to imagine, but let's kind of imagine it like from the perspective of, let's say, for example, we have a curve. And I think the curve might help us out to kind of think about what it might look like to have a limit and not have a limit. Now, I'm not too nitpicky with the whole, like, definition of the limit. We're not going to be doing any epsilon delta proofs in this class. What we are going to do, though, is we're going to think about the limit, and now we're going to talk a little bit about that limit and what happens as it approaches, or trying to figure out the limit as it approaches from different paths or different directions. Okay, so let's imagine that we have this, and this is a picture of a figure. This is f of xy equals x plus y squared. So if you want to think about this, it's got level curves of that are parabolas, and you can kind of see the parabola level curves in there too. And what I want to do is I want to notice this is my xy plane down here, and that's important. And the reason why is because this is where our disk is going to be. So I'm going to imagine, I'm going to just draw just generally a disk of radius delta around there. So there's my disk in the xy plane. Is that great? No, it's not perfect, but oh well, whatever. Okay. Now, what we're trying to do is we're trying to evaluate that limit as xy approaches 0, 0. And remember what I said at the very beginning. I said, look, one of the problems that we're going to have when we have functions with several variables is that we need the limits to agree from all of the different directions that we can approach this disk. Okay? So like, for example, if this right here, okay, this is my y-axis, and I'm like, okay, so on the y-axis, as I approach from the y-axis, or from the direction along the y-axis, okay, what do I get, right? And you'll notice that I hit 0, 0 right there, okay? Or excuse me, I hit 0. So 0, 0, that's the value inside of the xy plane. And the z value there, okay, the z value there, that's z equals 0. And that's what we hit. Now, if I come in from the x-axis, or along that path of the x-axis, what do I hit? Well, you'll notice it crosses again. It's going to cross at z equals 0. So we hit right there at z equals 0 again. So they meet. That's great. That's great news. What about if, say, for example, I'm coming in from the direction of, excuse me, this, by the way, this is, yeah, that's it. Let's say, for example, that I come in from the direction of like y equals x squared. Okay, so y equals x squared. So y equals x squared is coming kind of here, if you can kind of imagine it. And so y equals x squared, as I hit 0, 0, there it is, right? And what does it hit? It hits z equals 0 as well. Okay? And you'll notice that no matter which direction that I approach it from on the xy axis, every path is going to hit right in there at z equals 0. Okay? And in fact, it turns out that z equals 0 there. Okay? Or that our limit is equal to 0. By the way, this function, x plus y squared, is continuous at 0, 0. It's in fact continuous everywhere along the xy plane. And so consequently, it's going to have a limit everywhere. We're going to see that because we have continuity, because there's no issues with our domain here, that what we're going to get is we could just substitute in. We can just go in and do f of 0, 0 equals 0 plus 0 squared. Okay, and that just equals 0. Right? Continuous functions, you can just evaluate the limit because that's how they work, right? But what I wanted to do is I want to demonstrate that's what it looks like to have the function be continuous at that particular point. Okay? And, oh, excuse me, to have a limit where all the paths agree. That's really what I meant to say. That's a limit where all the paths agree entering in. You can imagine any path that I wanted to choose. I could choose to do, you know, like a cubic function, right? And that cubic function would still meet up, right there at 0, 0, because we have continuity right there. Okay? Now let's consider, what if f of xy equals xy plus y cubed over x squared plus y squared? We want to evaluate the limit as xy approaches 0, 0 of f of xy. Let's take a look at the graph. So now what we have here, using GeoGebra, we're actually going to take a look at, we've got this curve, and this curve is a bit different, right? You can kind of see that the curve is different. Now, one of the things that I want you to notice is take a look here. I'm going to kind of turn this around. Maybe I can show how this works. If you kind of look at, okay, there's a line, okay, there's a line coming through here right along this curve right here. Like there's like a loop, and it's kind of hitting above 0, 0. Okay, can you see that? So the limit, like along this path, whatever that path is, and we'll talk about what that path is later on inside of this lecture, whatever that path is, that line seems to be hitting that path above 0, 0. Now, if I turn it around a little bit, what you're seeing now, if I kind of come in here through that x-axis, is coming through the x-axis, I'm hitting at 0, 0. So you'll notice that in one case, we have a path that's kind of like, that the value as xy equals 0, 0, right, which is on the surface on the xy plane, okay, it kind of comes in somewhat above 0, the z equals 0, but like along y equals 0, we get 0, and along x equals 0, we also, it appears like we're getting 0. So it's only along that other path that we seem to be getting something different. And so that's actually really important, because that actually indicates that this limit does not exist. This limit does not exist because along two different paths, we get two different answers for our limit, right? And that's really important, because if you remember, in order for us to actually have a limit, for the limit to exist, it has to exist and be the same from all of the different paths as we approach. So this is an example of one in which we actually don't have a limit. We have a path that actually gives us a different value than all the other paths that we have on this surface. All right, let's determine now the limit, if it exists, for this. This is the limit of xy approaches 0, 0 of xy plus y cubed over x squared plus y squared. And what we're going to be looking at here, if you remember, this is the one where we saw that the limit in fact did not exist based upon the graph that we had. So let's go in and kind of figure this out. Well, what I'm going to do is I'm going to test out some different paths. And so some of the canonical paths, the paths that we'll try out, will be, say, for example, right, we're going to try out the limit from the direction y equals 0. Okay, so let's say, for example, from the direction y equals 0. Now, what we're going to do, notation-wise, is I'm going to make this now limit, and it'll be x, and then 0, because y equals 0. So I'm just going to actually then substitute in 0 for y everywhere in this equation. So the limit is x0 approaches 0, 0. And now this is going to be x times 0 plus 0 cubed divided by 0 squared plus, or not 0 squared, but x squared plus 0 squared. And if you notice, that ends up being 0 over x squared. So that's the limit, right, of x0 to 0, 0. But it's 0 over x squared, and 0 over x squared is always 0. It's actually constant. It's a constant function. And that equals 0, so which equals just 0. So that's what our limit equals from the direction y0. Let's say, for example, we go from the direction, okay, next direction we're going to use is going to be x equals 0. So now we've got the limit. We're going to substitute in 0. We'll keep y, okay, because y can be anything we want it to be. It's going to be variable, and it's going to go to 0, 0. And now I put that in, that's going to be 0 times y plus y cubed over 0 squared plus y squared, which is now the limit of 0y approaches 0, 0 of y cubed over y squared, which is the equals to the limit of 0y as it approaches 0, 0 of y. And what you can get here is now we can just directly substitute. That actually just ends up equaling 0 by direct substitution. Okay? It's now a function of just a single variable. It's a lot easier that way, right? Okay? Now, what about, let's try a different one. Let's try it from the direction of y equals x squared. Okay, so we'll try y equals x squared. Now we're along a parabola, which is interesting. It's an interesting direction. Okay, but it's still, theoretically, we would have to check it. We don't have to, but, you know, let's just say we're going to check it here. So now this is going to give me the limit as, and now y is x squared, so this is going to be x comma x squared goes to 0, 0. Okay. And it'll be now x times x squared plus x squared cubed divided by x squared plus x squared squared. And this is then x cubed plus, okay, x to the 6th divided by x squared plus x to the 4th. And that's our limit. I'll just write in limit for right now. You get that it's still x squared versus 0, 0. And so this is going to then be the limit, and we can factor out an x squared out of everything. So this is going to be the limit as essentially it'll be x approaches 0, but like x squared approaches 0, 0. And it'll be now, we'll pull out x squared, so that's going to end up being x plus x to the fourth over 1 plus x squared. Right? So if we pull out an x squared out of that, that turns that into a 1. That's a squared. That's a 4. And that's a 1. Okay? Now we can actually use direct substitution. Plugging in, we'd end up with just 0 plus 0 divided by 1 plus 0, which equals 0. Oh, it's 0 again. Awesome. So it seems to be that they're actually, like, you know, they seem to be agreeing. But we know that they don't, actually. We know that they actually do not agree. So let's go in and see, what if y equals 2x? Okay? Graphically, we kind of could have figured out that this is actually the path. But let's say, for example, we get y equals 2x. So I want to know the limit as, and we get x comma 2x approaches 0, 0. Okay? And I'm going to plug in here. Okay? I'm going to get, that's xy plus y cubed. So x times 2x plus 2x cubed divided by x squared plus 2x squared. And this is now 2x squared plus 2x to the sixth, so, or the limit, excuse me, as x 2x goes to 0, 0 of 2x squared plus 8x cubed divided by x squared plus 4x squared. And if I go in, I'm going to see that this actually ends up equaling, okay, the limit x 2x approaches 0, 0, and this is going to be 2x squared over 5x squared plus 8x cubed over 5x squared, which equals 2/5 plus 0. Right? Because these are going to cancel. This is going to become a single. That'll cancel. Okay? And then we have 8 times 0 is 0. So we get 2/5 plus 0. So this ends up equaling 2/5. Well, what we get here now is that when we take the path y equals 2x versus the path y equals x squared or y equals 0 or x equals 0, what we get instead is we actually get, instead, we end up with a different value for our limit. Okay? So the limit, as we get x, 2x approaches 0, 0, okay, of f of xy, does not equal the limit of, say, for example, x0 approaches 0, 0 of f of xy. Okay? So the limit does not exist. And that's one of the ways that we actually go through and we prove something like this. That limit will not exist. All right. There we are. Let's try another one. Okay, now let's take a look and let's evaluate this limit as xy goes to 0, 0 of x squared y over x to the fourth plus y squared. So now I'm going to take this and I'm going to actually, let's look at it along the path y equals 0. And so this is going to be the limit as we're going to go to x0 approaches 0, 0. And what we'll get is we'll get 0 over x to the fourth plus 0 squared, which is just simply 0 again. Okay? And so actually we find that along that path y equals 0, our limit ends up equaling 0. Great. Let's take a look at a different path. And now I'm going to look at this, and what I want to do is I want to actually think about it and say to myself, you know what? I could try out different things, but let's see if I can actually get it to fail. Okay? And if I look here, a couple of things that I want to notice. I want to notice that if I plug in x squared, okay, in here, then that, for y, if I want y equals x squared, then y squared will equal x to the fourth, and I'll get 2x to the fourth on the bottom, and I think I'm going to end up with x to the fourth on the top. And so consequently, I might end up with something that looks different than 0 over 0. So now let's try that out. Let's take along the path y equals x squared. Okay, and by the way, this is kind of thing that just takes some practice. You try out different ones that might work, that might not work. You know, you kind of look at it and go, oh, maybe this one will do it, maybe this one won't. right? Sometimes it's trial and error, all right? Because you may not be able to tell right off the bat. So we got this one. We're going to take the limit as xy approaches 0, 0. Okay? And it's going to be, or excuse me, x squared approaches 0, 0. And so that's going to then be x squared times x squared over x to the fourth plus x squared squared. And so that's the limit as x squared approaches 0, 0 of x to the fourth over, and this is now 2x to the fourth, which just ends up equaling 1/2. So now, on the one hand, when we come along the path y equals 0, we get 0 as the value for our limit, and when we come along the path y equals x squared, we end up with 1/2. And so, inevitably, that actually tells me that the limit does not exist. Okay? So, what we want to do here now, just to think about, like, kind of as a review, all right, when we're trying to find limits analytically, okay, right, we want to first start with substitution. Can we substitute? That's our first place to look. So, limits analytically. Then secondly, I'm going to ask myself, well, can I do some kind of algebraic manipulation that will allow me to, in fact, do substitution? And then 3, I'm going to pick some different paths. And in terms of paths, if you find yourself having to pick some paths, a couple of things to try: y equals 0, x equals 0, y equals x, y equals negative x. You might want to try also y equals kx, where k is some constant, if you can pick the right constant, or also y equals x squared. I mean, theoretically, you could be trying out like cosine x or sine x. I mean, it just depends. It depends upon the function that you're looking at, but these are some ones that you might want to try out. Okay, so try these out to see if you can actually basically get your limit to equal two different things when you're coming along different paths. And so that's actually how we're going to go out and figure out things analytically. Okay, when we talk about limits, okay, basically what we want to remember is the limit, okay, has to equal the same value along every path. All right, so any path that we choose, what we have to do is we have to see that the limit actually equals the same value. If it doesn't, if any of the two disagree, then what we have is in fact not a limit. The limit does not exist. All right, and so that completes our lesson.